But really what I want to get across is how what dark matter is and how we're thinking about it and how we might decipher this, even if we don't get to the meaning of life. Okay, so what is our universe made up of? Well, there's many ways you can ask that question, but this question can be asked in terms of who carries the energy in the universe. If we ask the energy that's driving the expansion of the universe, what is it made of? And this is sometimes referred to as the cosmic pie. It gives the sort of fractions of energy in the various components that we know about. The one that's labeled atoms is the stuff that's familiar matter, the stuff we're made up of, the stuff that we can see, literally see. And that's only 5% of the energy of the universe. You'll see the rest of it is what we call dark. Dark is actually a terrible name in the sense that this stuff is transparent. We see dark things. Dark things absorb light. This is stuff that doesn't interact with light. And by not interacting with light, I mean, if there's light, it just passes right through it. It's transparent, which means that dark matter, it's matter. What we mean by matter, it sounds circular, but it is what we mean, which is stuff that interacts with gravity-like matter. That is to say, it clumps, it's in our galaxy, it's around us. Dark energy is stuff, it's different, it's not matter, it's literally just energy. It's not made up of stuff. It's spread evenly throughout the universe. It's not clumping into structure the way dark matter does. Dark matter is made up of different stuff. It's not made up of atoms. It's not made up of the stuff that we study when we study elementary particles. It's not made up of quarks or electrons. It's a really new form of matter. And the question is, what is it? Before I get to that question, I just want you to know, I'm not expecting you to memorize this list, but when I talk about dark matter, a lot of people, get upset. They think, how do you know that you just didn't get the laws of gravity wrong? Because we don't directly see dark matter. What we see are indirect effects of dark matter. For example, the first one says galactic rotation curves. What that means is when we look at stars in our galaxy and in other galaxies, we see they're moving faster than can be accounted for by the matter that's there. So we don't directly see the dark matter, but we see that there has to be more matter than we can account for. And there's many different ways in which we observe dark matter, and that's important because when people try to modify gravity to account for dark matter, they can usually do one or two of these things at most. They can't account for all of them. There is a consistent theory which just says the simple fact that the matter we're made up of is not all the matter there is. For some people, that seems very disturbing and surprising. You would think since the time of the Copernican revolution, we should be a little bit more open-minded than that. I mean, we know if this matter exists, we literally cannot see it. It doesn't interact with light. So there's no reason it shouldn't be there. In fact, the more surprising thing is that the amount of dark matter and ordinary matter are so comparable that you can both see them both on that picture of the pie I had before. So I'm not going to go through the rest of the list, but I am going to talk a little bit about what's there. And I just want to remind you that, and so I'll do a demo now where you have billions of dark matter particles going through you. You're probably not aware of it because you don't see them and you don't interact with them. And so really, people ask where dark matter is, it's all around. But where it really is, as I'm going to get to, is in terms of our galaxy, it basically surrounds us in an enormous spherical halo. And I'll get to that in a minute. And I just want to emphasize that even though we don't see it, and one of the reasons I like studying science and I like talking about science is I think it's really important in terms of giving us a perspective on the universe. It really makes us think about what's out there in different ways. And we realize we're not making up everything, but even though we don't directly see it, our galaxy wouldn't even exist in the lifetime of the universe had there not been dark matter that collected and allowed ordinary matter to come along with it. So it was essential. So it's one of these lower classes that we don't notice, but it's actually responsible for the structure in our universe. And as I said, it surrounds us in our galaxy in an enormous spherical halo. And that's generally what happens. You can literally, in some sense, look under the lamppost with respect to dark matter because all matter interacts with gravity the same way, which means that when dark matter collapses, ordinary matter collapses along with it. So even if we don't see the dark matter, we do see visible matter in galaxies, but that visible matter in some cases, like in our galaxy, is mostly collapsed into a disk, the disk of the Milky Way that you see on a clear, dry night. That's because ordinary matter radiates. So again, dark matter is in the galaxy. It's basically in a halo, approximately spherical structure. But ordinary matter radiates. It cools down. It gives off energy. It cools down and collapses. And that's why it ends up in the Milky Way disk. If you were ever wondering why there's a Milky Way disk, that's the reason. Now, okay, this is all stuff that is known about dark matter. And I really hope you understand that we really believe dark matter is out there. What we don't know is what is it? And by what is it, I mean, is it an elementary particle? If it is a particle, what is that particle in the sense of what's its mass? Does it have any interactions? Does it have a little bit of an interaction with ordinary matter we haven't seen? Does it have its own light? Does it interact with itself just the way we have light that dark matter doesn't see? Maybe it has its own light. Is it just one type of particle? And I think, again, this is really a good time to reflect on how we think about foreign things, foreign species, foreign whatever. Because most physicists assume that dark matter is one thing, and it basically has very little interactions. So we ask the question, what if it did have interactions? What if it is made up of more than one thing? Doesn't mean we know it's true, but what our perspective is that if this were the case, we would have a good chance of finding it with existing measurements, and I'll tell you about one of them. So if there are existing measurements that can find it, we'll only find it if we know what we're looking for. That might seem like an overstatement, but the fact is, when you're looking for subtle effects, it really helps to know where you're looking. It does not so much that you bias the thing to find things that aren't there, but if you don't look, you'll just miss it. And there are ways in which we can find out if dark matter has an interacting component, and by looking in detail at structure. So we asked ourselves, suppose, for example, there is a small fraction of dark matter that has its own light. Not all of it, but say some of it does. Then there would actually be a disk of dark matter. Just like there's a ordinary matter in a disk, maybe there's dark matter in a disk. Now, why would we care about this small fraction? Precisely because we could learn about it. We can find out something. Even if we don't see most dark matter because it's basically not interacting, if there is a component with interactions, we can learn about it. So we can at least say whether or not it's there because we can ask the question. And in fact, one of the most exciting ways of observing this is through something called the Gaia satellite. The Gaia satellite is just great. You know, I have to say, as a particle physicist, we were very excited because when you do particle physics, you might have to wait decades before things are tested. We had this idea, and that very fall, the Gaia satellite was launching. And what the Gaia satellite does is it measures the position and motion of 1 billion stars in the Milky Way. That's a lot of stars, and it's enough that you can learn about the gravitational potential of the Milky Way. You can learn a lot of other things too, but you can learn about the gravitational potential. And in particular, if there is a dark matter disk, it would exert a gravitational influence that would be reflected in the motion of stars. So this existed before our research. It was going up, it was doing this, but what we're pointing out is you can actually learn whether or not this exists, or if it does exist, what are its properties. So you can look at the data a little bit differently and learn about it. So I like to do what I call model building, what we call model building, which is we hypothesize what might be there beyond the things we know. We want to understand very well what we know, but we want to say, how do we go beyond that? Okay, but here's the crazy other consequence that led to the title of the book, and also some really interesting explorations for me about Earth. But here's the story. So this picture is supposed to roughly represent the motion of the solar system through the galaxy. The solar system rotates around the galaxy about every 240 million years. But as it does so, it bobs up and down a little bit, kind of like horses on a carousel. It bobs up and down through the plane of the Milky Way galaxy. Now, why would we care about that? Well, every time it goes through the plane of the galaxy, if this dark matter disk exists, it would exert a little bit more of a gravitational force, a little bit of a tidal gravitational force, a little bit of a kick. Now, why would we care about the kick? Well, it turns out the solar system, you've all learned about the solar system in high school, but our view of the solar system has evolved a lot. And instead of it's not just planets, it's also things that are moving. It's asteroids and comets. The source of what are called long period comets, comets with period more than 200 years, is something called the Oort cloud. The Oort cloud is thousands of times farther away from the sun than the Earth. What that translates into is it's much more weakly gravitationally bound to the sun. So if something even gave it a little bit of a kick, it can kick it out of the solar system or can enhance the probability that it comes to hit Earth. You can actually go on the internet and look up something called the Earth Impact Database, which tells you every crater from an impact that has been found on the Earth. And in the last 250 million years, there's been about 27 of these that are bigger than a kilometer in size. So big ones. So big impacts that have occurred. And if these big impacts occur, it turns out that most stuff hits the Earth all the time. I have a table in the book. I could show it to you later. That stuff hits the Earth all the time. But it looks like there's a little bit of an extra probability for big stuff to hit periodically, about every 30 or 35 million years. And so big stuff, I mean stuff, bigger than a kilometer at least. So really, big things hitting the Earth. So it looks like there's a little bit of a probability that that's true. And the question came up, what would cause periodic impacts? And so that picture is telling you what would cause periodic impacts. If there really is a thin disk of dense dark matter, every time the solar system passed through, it could kick something out of the solar system. Now, does this mean it's right? Not necessarily. What is interesting, though, is that, of course, we do know things hit the Earth. I like this picture just because it's beautiful. It's not the one that corresponded to the one that killed the dinosaurs, but we do know that an impact was associated with the extinction of the dinosaurs and 2/3 or 3/4 of the species on the planet in something called the KPG extinction 66 million years ago. 66 million years ago actually works very nicely with this periodic motion because it turns out the solar system went through the plane of the galaxy about 2 million years ago, and if the period is 32 million years, it would correspond very nicely. Do we know this is true? Not necessarily. But if it is true, we know what the properties of the dark disk would have to be, and we can use the Gaia data to study that. So I'm not claiming we know this. What we do know is that there's dark matter. What we do know is that there's a possibility for studying what dark matter is in our galaxy. And what we do know is that there was an extinction that happened 66 million years ago that was associated with an enormous impact. And actually that story, I wish I had more time because I would love to tell you the story of how we actually discovered that it was an impact and found the crater associated with that impact. At the time the hypothesis was made, we actually hadn't found a crater, so we couldn't test the theory really. But after some very, very clever work and in conjunction with Pemex, a Mexican oil company, the crater was discovered, and it's in the Yucatan. And this is just me studying the layer of rock that shows you the extinction. And since I'm out of time, I can't tell you about that now, but you can read about it. So I just want to say that in my book, there were a number of general lessons in addition to the actual science. I tried to take you through, because a lot of the time the kind of science I'm doing seems so disconnected from life on Earth. And I wanted to point out the many connections between how the universe evolved, how the galaxy evolved, how our solar system evolved, how life evolved, and how we are connected to the universe that's around us, which we miss a lot of the time. And because we miss it, we sometimes are a little bit sloppy with our planet. So there were these general lessons that I had. I mean, usually when I'm writing these books, I want to just focus on how we understand things, what they are. But there really are things that are amazing about our world, and a lot of them we do want to preserve.